We will now see how you can calculate this integral using a clever technique. Let us denote the area under the curve here from a to x as capital A of x. So if you have x here and x plus h here, where h is some positive value, then we get an area here, and that's just the complete area, ax plus h, minus this part here, the blue part. So the area of this pink part is given by this. If we now let h be a small number, this is basically a trapezoid. And since h is small, the distance between these is small, this trapezoid we can just calculate as the area of a rectangle here. So we have that this area is roughly equal to the width of the rectangle times the height of the rectangle. So we get this equality. So if we divide this one both sides with h, we get this one. And if we now take the limit when h goes to 0, this will be exact. So we just get this equality. But here on the left side, we see that it's just written the definition of the derivative of a. So this is just equal to the derivative of a. So the derivative of a is just equal to the function. But this here means that a of x must be an antiderivative of this one. We thus have this. Since a of x is the area up to here, if we put x equal to a, then we just get the area from a to a, and that's 0. Then we have from this one that this will hold. A of a is equal to 0, at the same time is equal to this, where we put in x equal to a. So f of a plus c is 0. But this here just means that c is equal to minus f of a. And putting that into here, we get this one. If we put x equal to b, then we just get this one. But this here, a of b, that's the area under the curve here from a to b. So this one is just equal to the integral of the function here from a to b. So this is equal to that, which means that this is equal to this. And then we have arrived at this formula. So by using this formula, you can calculate the integral of a function just by finding an antiderivative of the function. And then you put in the endpoints into this antiderivative and take the difference. So let us take an example of how to use this. So let us say that we want to calculate the area under this curve here, 2x plus 1. On the one hand, this is just a trapezoid. The area of a trapezoid is just given by this formula, where c is the length of this side, d is the length of this side, and h is the height. This length we get by putting in 1 into the function here, we get 3. And the length of this side we get just putting in 4 into the function here, we get 9. And the height is just 3. So this is just 18. But we could also use this formula to calculate the area under the curve. And in this case, a is equal to 1. And b is equal to 4. And f of x is this one. Then we need to find an antiderivative of this. But that's just x squared plus x. So this one. And now, in this case, we only need one antiderivative. You don't need the most general one. So you don't need to add a c here. And even if you would have added a c here now, they would cancel. So here we want to put in b into the antiderivative. So that's just 4 squared plus 4. Then we put in 1 into the antiderivative. So we get this. And this is just 16 plus 4. And this is just 2. So we get 18. And that's just the same as we got geometrically. An alternative way of writing this is this one. So this is just a notation for that. So per definition this means that. And by introducing this notation, then instead of writing like this, you can just write it like this. Remember now that this is just the area under the curve here from A to B. So this part here of the left hand side here, that's basically the area under the curve before we have determined the starting point and the end point. So this is just an area of an undetermined interval. Since this is equal to that, and if I haven't decided on A and B here, we haven't decided on A and B here, then basically we have this. And we just forget about these parentheses for a moment. We see here that we have this one. And here's some motivation for why we used this symbol to denote the antiderivative. So we see that it's natural to denote antiderivative by this symbol since it's connected in this way. In this case we have decided on the limits A and B. So this is called a definite integral. Here we have not yet decided on the starting and end point. So this is called an indefinite integral. So an antiderivative can also be called an indefinite integral.